Back to the beginning, a journey to the start of the cosmos. SuperQuest, beyond the contest, it's not just the winners who benefit. Casting without a crack, simulation to the aid of big steel. A cloud upon the forest, probing tree damage from acid rain.
There aren't any bigger questions than what's the origin of everything.
The sun, the moon, and the stars. Bodies of great beauty and equally great mystery, they have been our most visible link to the vast universe since the beginning of time. But at Princeton University's Peyton Hall, astrophysicist Jeremiah Oestreicher leads a search into an even earlier time, a time just before the structures of the observed universe had ever appeared.
The metaphor I think of that's simplest for me is you're standing on the beach and you see the breakers coming in, breaking on the beach. You say, where did this come from? It didn't come from nothing. Well, the analog of the breaking waves is the formation of all the structure we see around us in the form of galaxies, clusters, tremendous variety of structures, and each observational survey shows more. Where did it come from?
To better understand this question, Oestreicher began developing a computer model that could recreate the formation of the structures in the early universe. Previous models had focused primarily on the physics of so-called dark matter, an invisible matter thought to make up 90% of the mass of the universe. But Oestreicher, along with graduate student Renyu Chen, decided to try a different approach, a computer code that incorporates the principles of hydrodynamics.
I used to say when I went to conferences, I know this code is right because I got here. And if the code was wrong, the plane would have fallen out of the sky. If you want to understand the flow of air past an airplane wing, and how hot the plane will get, what the lift is on it, that is hydrodynamics. We took computer codes for the flow of air past airplane wings, essentially, and other similar problems, and modified them to use for cosmological applications.
But the adapted hydrodynamics codes required much more computer power than the Princeton team had available, and they were looking for more advanced hydrodynamics codes to plug into their cosmological model. They found both in a collaboration with University of Illinois astrophysicist Mike Norman.
Numerical cosmology simulations are very compute intensive. You take a large chunk of the universe and you subdivide it into little volumes, and then you evolve the equations for the hydrodynamics, the dark matter, and gravitational forces in each of those little volumes. The more cells, as they're called, the better you can describe the evolution of this chunk of the universe.
Himself an expert on hydrodynamics, Norman worked with the Princeton group on refining their codes to run on NCSA's multiprocessor convex C240 and developing the means to visualize the results. This demanded coupling the convex with a powerful SGI graphics computer. Working with research programmer Chris Song, Norman then embarked on a journey never before taken, a visual journey back more than 10 billion years, back to when the universe was first forming. Using the Princeton data, they began to work on developing visualization software. The result, a package called the Cosmology Explorer, and a glimpse at how the universe may have begun.
Once we got the data, and once we had the visualization software working, we got swept up in the scientific discovery process, and it was very exciting to see what was happening there. We were the first to ever see the predictions of a cosmology simulation as to galaxy formation, when and where and what happened next. When you look at the visualization, what you see initially is an empty box, because there are no galaxies in the early universe. And then as time goes on, you start seeing the galaxy particles appearing. We've color-coded the particles according to their date of birth. In other words, when in the history of the universe were they formed, so that we can answer the question, where did the galaxies come from that end up here, where here may be the center of a cluster of galaxies or on the periphery.
But a nagging question remains unanswered. If the universe had indeed been formed by a huge uniform explosion or a big bang, as most scientists believe, then where is the evidence for irregularities in the distribution of energy deemed necessary to explain the universe as observed today? The answer could come from NASA's Cosmic Microwave Explorer Satellite, or COBE. Measuring microwave radiation far into deep space, and therefore far back in time, COBE uncovered slight irregularities, ripples in the microwave radiation left just 300,000 years after the Big Bang. For the first time ever, astrophysicists had tangible evidence of the seeds from which the structures of the cosmos evolved.
The COBE results are revolutionary for cosmology. What they do is they provide you with the imprint of creation. This is basically what the early universe looked like before the galaxies were formed. And it is out of those ripples, which are really density perturbations in the early universe, that the galaxies and the clusters of galaxies formed. So in terms of theory, what it means is that we have the starting conditions for the universe fairly well constrained for the first time.
Armed with knowledge of these new starting conditions, Norman and Ostreicher are jumping headlong into the future. A more accurate hydrodynamics code is now being developed as the scientists prepare for the largest, most sophisticated cosmology simulation ever. These computations will be run on NCSA's newly arrived convex C3840, and their success may provide further insights into one of mankind's oldest mysteries.
We've made much larger scale simulations with much more detail, much of a huge variety of different scenarios which no one had ever tried. And that's just because of the computing power, that it's available and easily used at the supercomputer centers.
Mankind has always indulged in creation myths, and as far back as recorded history goes. And it's just human nature to want to understand the universe we live in, where it came from, what it is now, and where it's going. With the Big Bang Theory in its recent verification, or vindication, I would say, through the COBE results, we now have a fairly detailed creation myth become science.
Last year, NCSA RealTime reported on SuperQuest 1991, a National Science Foundation-funded high school science competition. 11 winning teams of high school students and teachers had attended 3 weeks of intense summer training at one of 3 major computational science facilities: Cornell Theory Center, the Alabama Supercomputer Network, or the National Center for Supercomputing Applications. But the Summer Institutes marked only the beginning. The students returned home with the computational skills required to pursue their science projects. We recently visited 3 of the winning students at their home schools, where it became clear that the SuperQuest experience not only benefited them, it could also enhance the high school curriculum as a whole. To begin with, the program linked computing in the classroom to real-world applications. Montgomery Blair High School, Silver Spring, Maryland. Ben John is tackling a major engineering challenge: programming robots to navigate a given space.
This is an ultrasonic transducer which sends and receives ultrasonic sound. It takes a simple distance measurement and is rotated around by a computer-controlled platform, so I can take distance measurements in all directions. The computer can analyze a returning sound wave, like bat sonar, and find out what the room looks like.
As part of her SuperQuest adventure, Tracy Spiegner from J. Oliver Johnson High School in Huntsville, Alabama, assisted NASA scientist John Campbell in prototyping an X-ray telescope.
Basically, I had to start out with 2 grids and figure out what point the photon is going to enter it in, where it's going to land at on the second grid, and there's a detector right behind the second grid, so I got to figure out which ones will go through and which ones won't.
Patrick Chan, a SuperQuest team member from James Logan High School in Union City, California, developed a program to simulate traffic congestion.
With this program, I can predict at what time, at what street there will be a traffic jam.
When coupled to scientific visualization, the transformation of numerical data into graphic images, computer simulation enables high school students to explore science creatively and interactively.
We got 16-year-olds and we're giving them the keys to the biggest supercomputers in the world and saying, go do stuff, try new things, play around, have a good time, try to do some science. And it's very exciting. It's exciting for them, it's exciting for us. kids can do this work.
Meeting the challenge of computational science helps spur many students toward choosing a scientific career.
That's what SuperQuest can do for us at high school level. It can jump them past college to the real world and give them a taste so that maybe in college they'll know what to look for. They'll know what to do. They'll know what to specialize in.
At the heart of the SuperQuest experience, the mentors. Each team member establishes a working apprenticeship to a scientist specializing in the student's area of research. By encouraging such interactions, SuperQuest cultivates a direct link between high schools and the scientific research community.
You can't be expected to know all about physics, all about chemistry, all about biology. So at the heart of our program are the mentors, and we rely on them to help the students know the science or learn the science behind what they want to do.
It was fun being at NASA because, I mean, there's so much that I could work with out there that I don't think there's any other place I could find it.
She seemed very enthusiastic, and she was very eager to learn and highly motivated.
We built like all these telescopes, and I look and I'm like, oh, this is amazing, you know, and I found out all this goes into it. And this is just a computer model, so mine was kind of simple. And so when I think about the workings of actual telescopes like this, I think, boy.
Mentoring is not only for professional scientists. It's a role Ben Jun and SuperQuest graduates like him can perform in their own schools.
And we need to get that installed on the RS-6000. Is that something that you can do sometime within the next week or so?
We have some help we can do. I try to always act like a mentor and help people use the supercomputer, the resources, and try to train people to help them use the computer systems as soon as I'm gone. I'm fairly confident now that the flag of SuperQuest will keep going, at least with my school.
We have developed 2 brand new courses, complete whole new courses, revolving around computational science and modeling and simulation. Those have been a direct result of our involvement in SuperQuest and what we've learned from being in that program. The regular courses that we teach here have all incorporated computational techniques, visualization, use of supercomputers, use of high-performance machines as an adjunct to or an addition to the regular curriculum.
Computers and effective software transform the desktop into a virtual laboratory. To support their team's advanced training, SuperQuest schools receive workstations, software, and a connection to the Internet, a national and international computer network. Linked to the network, students and teachers can interact with peers and with the global science community.
If I was having a problem with a course or needed an idea, you could ask a question of someone across the United States that might be teaching something similar. And we could communicate and work together.
What we have learned is that these kids are absolutely capable of using this technology. They're very creative. They teach us a lot. The kids will learn things and they'll teach us.
It's a way to get them turned on to more information. And they really do get turned on, and they like to do it. You say, you spent all night researching this? And they go, yeah, but I wanted to. That's the kind of thing that I've seen with the power of supercomputing.
Steel, once a shining example of American industrial dominance, the American steel industry has fallen on hard times. Increased competition from foreign steel makers has tarnished its once bright future, resulting in plant closings and job layoffs. Faced with tougher and tougher economic times, how can the industry find the resources necessary to help restore it to a worldwide competitive position?
This is one sector of the U.S. economy which is taking quite a beating from both the Europeans and the Japanese. In general, U.S. companies are somewhat leaner in the research area. On the other hand, we have a much larger body of expertise in the universities which could help industries a lot if we tried to work with them.
Nucor Steel is a relative newcomer to the American steel industry. Nucor's Crawfordsville, Indiana plant was built around an untested, brand new technology known as thin slab continuous casting.
Our caster is quite a bit different than the conventional casters being operated in industry today. The heart of the process, and in fact the heart of this whole plant, is the continuous casting mold. It's a revolutionary design, and Nucor was the first commercial outfit in the world to adopt this technology. In so doing, Nucor took a pretty big risk putting $300 million into a greenfield site with no actual guarantees that it would be able to produce a commercially acceptable product.
The Crawfordsville plant has been successful in producing flat-rolled steel, but not without some problems. Surface cracks began appearing prematurely on the face of the costly mold sets.
The biggest problem we were having with the mold is a much shorter useful life than we had anticipated, so we were looking for anything that would increase that life.
Meanwhile, unknown to Nucor, at the University of Illinois, a possible source of help was already at work. Mechanical engineering professor John Danzig was independently conducting research of his own into the continuous casting process.
Hi, John. I just finished up those the new temperature results.
Along with graduate student Tom O'Connor, Danzig obtained the patent information for the Nucor mold and began developing a three-dimensional model. Utilizing one of NCSA's Cray supercomputers, Danzig and O'Connor conducted simulations of temperature, pressure, and stress in the mold. The analysis of the temperature distribution throughout the mold revealed some intriguing results.
Initially, we could tell that the molds were running very hot, about 150 degrees hotter than conventional slab casting. We weren't really sure, what the effect would be, so we could tell from the high temperatures in the mold that there may be some problems with the mold itself.
Determined to obtain real-world feedback on the direction of his modeling, Danzig arranged a meeting with Steve Wigman and Mark Millett, the melt shop manager at Nucor Steel. Neither party was prepared for what the meeting would reveal.
We started to show them some of our results, and suddenly they became very interested because we were showing them calculations which looked an awful lot like things that happened in their process that we had no way of knowing about.
We were surprised that people from the university who have never seen our mill or our mold in actual operation could so closely simulate what was happening out here.
Danzig's thermal models had accurately predicted the areas in the mold where the cracks had indeed formed. Wigman then provided more details of Nucor's process, enabling Danzig to fine-tune his model in a search for the cause and a possible solution to the cracking problem. Danzig and O'Connor evaluated the way in which the mold is currently bolted in place and then designed an alternative.
We changed the boundary conditions by saying that instead of bolting these positions on the back, if we were to allow those to expand in this direction, so that if the mold gets hot on its face during casting, it's free to move in that direction to accommodate that.
He then calculated the stresses and strains on the mold under both the current conditions and with the new constraints.
You see that this red region here and here are areas where there's large tensile stress, and these correspond very closely to the locations where cracks are seen in the molds. The legend is the same for both cases, so you can see that both the magnitude and the extent of the high stress region is considerably smaller in the new mold design than it was in the earlier one.
Danzig's modeling laid a firm foundation for optimizing mold performance and durability. With new mold designs being developed at Nucor, Danzig's simulation data could eventually help boost the company's market share and bottom line.
We feel that if the process can be modeled so accurately that there's hope of making improvements in the mold design by taking advantage of what we've learned in the modeling process. It brings a new level of analysis to our problems. It's something that I don't anticipate that we will ever have internally. So we will be dependent on people like John Danzig to come in and offer this type of help.
I think it's very important for universities to be able to interact with industry, especially in the engineering area. It's very easy for us to sit in our office and think up problems which have nothing to do with what are the real problems in industry. Because of that, there's a lot of talent in universities that doesn't get applied to important problems that reflect on American competitiveness in the manufacturing sector. This is a very rich area for us to improve what we do.
An ancient forest wreathed in mist, a brief glimpse of another age. Inside the woods, the trees beckon the eyes skyward to the canopy. These trees of the Pacific Northwest are old, some dating back to the time of Columbus. Over the course of the year, each transports tons of water from earth to treetop and converts light to food. When at last a tree begins to die, to human eyes, the dying is invisible, often occurring over decades, which makes it difficult to pin down if the dying is natural or a result of stress from other causes, such as pollution. In 1986, the Environmental Protection Agency, concerned that industrial sulfur emissions and nitrogen oxides dissolved in acid rain might damage the forests of the United States, formed the National Acidic Precipitation Assessment Program, or NAPAP. Ross Keister, a research scientist in the Forest Service, was appointed by the EPA to organize the Synthesis and Integration Program within NAPAP.
The idea of the Synthesis and Integration Project was to bring together all of the information that something like, in the end, 110 different principal investigators were creating, bring that information together and focus it on the policy questions that were at hand, which had to do with whether or not we needed greater regulations of sulfur and nitrogen emissions and hence deposition.
The ultimate goal of the project, to submit a document to policymakers that would quantify possible damage from acid rain. A three-pronged approach was adopted. 1, documentation collected in field surveys. 2, data obtained by experiment. And 3, computer models that integrated all the resulting information and simulated the potential impact on forests. David Ford is director of the Center for Quantitative Science at the University of Washington in Seattle. An expert in modeling tree physiology, Ford was brought into the project early on.
But what computer modeling allows you to examine is a whole range of different scenarios, so that one could simulate the effect of a certain reduction in foliage, which might be equivalent to a certain estimate of acid rain effect, and then examine all the way through how that would affect perhaps bole increment, foliage increment, branch increment, and then try different combinations of those in the model as though it were real experiments.
Keister asked Ford to develop models revealing the growth and reaction response to acid rain in both red spruce in the northeastern United States and loblolly pine in the south. To develop appropriate algorithms, Ford exploited an ongoing collaboration with the forest ecologist at the University of Washington. This stand of Pacific silver fir in the Seattle watershed has been the subject of a 15-year investigation. Doug Sprugel measures new growth in the densely packed trees, while Tom Hinckley records the data. Nearby, their colleague Renee Brooks is measuring the rates of carbon dioxide exchange in fir needles, thereby obtaining data on possible changes in the underlying mechanisms that power the tree's system.
What I'm doing is I'm measuring gas exchange of the foliage, and I'm measuring a range of different age classes of foliage. There's up to 10 or 15 years of different age classes of foliage on these trees, and I'm measuring the foliage respiration photosynthesis in different light environments.
To integrate the field data, Ford developed the complex algorithms to be later used in the simulation studies. Employing a network link to the Cray YMP at NCSA, Ford, assisted by programmer Ann Avery, then developed realistic computer models adaptable to forests elsewhere. This graphic displays a competition model and depicts an aerial view of the stand in the Seattle watershed. Generated with the aid of NCSA-developed software tools, the graphic illustrates the growth patterns of the trees over a 15-year period.
The essence of the model is that the light is simulated to come down onto the forest and it's absorbed by foliage. That's then transferred into an estimate of photosynthesis and growth. So you can calculate for each tree how much photosynthesis it's got and how much growth it could make.
And that's one of the real powers of the high-speed computation, is that you don't want to grow just one tree and make your conclusions from a simulation run on one tree. You want to grow hundreds of trees, and that's indeed what we did in the simulation process, so that you can say something about the behavior of an average tree and about the variation or the variance in the behavior that you see across a population of trees.
The simulation indicated that the cumulative effect of acid rain over time would indeed damage red spruce.
As the damage due to the acidity increased, the trees became susceptible to higher and higher midwinter temperatures. And so that the possibility of damage was increased from 1 year in every 10 when the temperature dropped below a certain point to 1 year in every 8 as it dropped to not quite such a low point.
The simulations further predicted that ozone pollution, in part linked to sulfur emissions, would similarly cripple loblolly pine in the south. This evidence, along with independent data obtained by other researchers, played a part in the reauthorization of the Clean Air Act of 1990. The provisions of the Act state that sulfur dioxide emissions must be cut by 10 million tons annually by the year 2000, while nitrogen oxides are to be cut by 2 to 4 million tons annually, with additional limits established in 1997. Although the old-growth forests of the United States are still threatened by habitat destruction, industrial compliance with the Clean Air Act could help trees, as well as human beings, breathe a little easier.
Ecology is about systems open to many, many different types of influence. It's never a science which is going to be totally conquered by the experimental method. We're always going to have to be examining, well, what would happen if temperature was increased? What would happen if this occurred? What would happen if that occurred? That's the very nature of ecology. And models are well suited to investigate those types of questions.
If you would like to know more about the activities featured in this program, please contact NCSA at the following address.